Ever wondered how we go from a high voltage to a lower one without wasting energy? Imagine you want to power a 5 volts device, but you only have a 12-volt battery available. A buck converter is just what you need. This is All My Circuits. In this video, we're going to use LTspice to look at the basic operation of a buck converter and answer a few simple questions. What is the output voltage value when we apply a fixed switching pattern? How does the inductor behave? What does the output voltage look like? Let's build a simple model and see what we can learn. Here's the basic buck converter circuit. It includes a DC voltage source, an ideal voltage-controlled switch, a diode, an inductor, a capacitor, and a resistive load. We also needed to define the following values to operate the simulation: an input voltage of 24 volts, a switching frequency of 10 kHz, a duty cycle of 50%, an inductor of 1 millihenry, a capacitor of 1 millifarad, and a load resistance of 10 ohms. Let's run a transient simulation for 200 milliseconds to allow the output to settle. While we wait for the simulation to complete, let's remember that the output voltage is given by the duty cycle multiplied by the input voltage. The switch is controlled by a pulse voltage source applying logic state high equal to 1, meaning close switch, logic state low equal to 0, meaning open switch. If we plot the input and output voltage across the capacitor, we should see the output voltage settling at around 12 volts. That's half the input voltage, consistent with a 50% duty cycle. Before we look at more waveforms, let's adjust the time base so we get rid of all the oscillations at the beginning of the plots. The inductor current forms a triangular waveform, meaning that it's storing and releasing energy at each switching cycle. Finally, we can see a small ripple on the output voltage due to the capacitor charging and discharging. The current and voltage waveforms have interesting shapes, so let's look into them in a bit more detail. Why is there current ripple in the inductor? We need to spend some time looking into the behavior of the inductor. Inductors resist changes in current, but they don't keep current constant. Instead, they ramp it up or down depending on the voltage across them. Looking at the voltage across the inductor will help us understand more about the current ripple. Let's change the simulation settings to avoid showing the oscillations at startup. We'll set the simulation time to 200 milliseconds and tell LTspice to only plot the last millisecond. Let's run the simulation so we can start looking into some waveforms. First of all, the switch is controlled by a pulse signal at 10 kHz and duty cycle 50%. We can plot the command and see that the switch is closed when the command is high and the switch is open when the command is low. When the switch is on, point M is at the same voltage as the input. The other end of the inductor is connected to the output voltage. So, the voltage across the inductor equals the difference between input and output voltage. In our simulation, that's 24 volts minus 11.6 volts, so 12.4 volts across the inductor. If we plot the inductor current, we see that the positive voltage causes the current to ramp up. When the switch is off, the diode conducts and the inductor sees a negative voltage given by the output voltage plus the forward drop on the diode. Since our output voltage is roughly 11.6 volts and the forward voltage on the diode is 0.8 volts, the voltage across the inductor is negative 12.4 volts. This causes the inductor current to ramp down. So the ripple in the inductor current comes from the applied voltage across the inductor during each switch cycle and follows the inductor equation. Now that we understand the current ripple, let's look into the output voltage and see if there is a relationship between the two. Why is the output voltage not perfectly flat? Why is there still a little ripple? Similar to inductors, capacitors resist changes in voltage. They don't keep the voltage constant. Instead, they charge or discharge depending on the current flowing through them. If we plot the output voltage, we might think the ripple is huge. Let's adjust the vertical scale to something more reasonable. In reality, it's just a small oscillation on top of the average output voltage, but it's still important to understand where it comes from and what causes it. Let's set the output voltage aside for a moment and plot the inductor current. We know that the average value of the inductor current is equal to the load current, which we can assume to be essentially constant without affecting the accuracy of our analysis. This means that any difference between the inductor current and the load current must flow through the capacitor. The capacitor charges and discharges with each switching cycle, and it's the AC component of the inductor current that creates the ripple on the output voltage. Let's see if we can calculate the output voltage ripple for our circuit using a simple formula. If you're curious about where this formula comes from, check out the video linked in the top right corner. It explains the derivation really well. We know that the amplitude of the capacitor current ripple is roughly 610 milliamps. The switching frequency is 10 kilohertz, and the output capacitance is 1 millifarad. Plugging those into the formula gives us a calculated voltage ripple of 7.75 millivolts. If we enable the cursors on the output voltage trace, we can see that the simulation result is pretty close. Now that we have a basic understanding of the buck converter operation in steady state, we can go back and take a look at the startup oscillation. Why is there an oscillation at startup? Let's change the simulation settings to show the full transient at the beginning of the simulation. We already know the output voltage eventually settles into steady state, so we'll reduce the simulation time to 30 milliseconds to focus on the oscillations. Let's hit the Run button and look at some waveforms. If we plot the output voltage and inductor current, we notice a large swing right at the start. That's the LC network finding its natural mode. This occurs because the inductor and output capacitor form a simple LC tank circuit. When a step input is applied, in this case the PWM signal starts abruptly, it excites the resonance at a frequency determined by the inductor and capacitor values. Given a 1 millihenry inductor and a 1 millifarad capacitor, we expect the LC network to resonate at approximately 159 Hz. We can verify this in our simulation by performing a Fourier transform of the output voltage and observing a bump in the magnitude spectrum around 160 Hz. If you've been following along, you'll know the resonance frequency depends on the values of inductance and capacitance. Let's experiment by changing the inductor and capacitor values to 500 microhenries, microfarads, 1 millihenry, millifarad, and 2 millihenry, millifarad, then rerun the simulation. What we observe is that the L and C values significantly affect the resonance frequency, but they don't seem to have much impact on the amplitude of the voltage overshoot. We can annotate the plot to improve readability. Now let's try something different. We'll add some resistance to the circuit by including the series resistance of the inductor. We'll define a new parameter, LSR, and sweep its value from 0 to 2 ohms in step 200 milliohms. Don't forget to reset the inductance and capacitance back to 1 millihenry and 1 millifarad. We can see that the voltage overshoot is greatly reduced by introducing some damping, especially for high resistance values. Let's annotate the plot to see how damping is affected by the resistor values. Adding damping clearly helps reduce the overshoot. However, the trade-off is a reduction in efficiency, since the damping resistor causes losses not only at startup, but also during steady-state operation. So now we understand what causes the oscillation at startup, and we also see that simply adding a resistor isn't a good long-term solution because it reduces efficiency. But why is that, and how do we evaluate efficiency? What affects efficiency? As usual, let's start with the simulation setup. It's helpful to introduce explicit resistors into our simulation to represent the series resistance of the inductor and capacitor. We'll set both values to 50 milliohms and run the simulation using the usual command with startup disabled to skip the initial oscillations. LTspice can plot instantaneous power by holding the Alt key and clicking on a component. Let's use this feature to measure the power delivered by the input supply and consumed by the load resistor. Note that we need to invert the sign of the input power plot, since LTspice conventionally treats the current exiting a voltage source as negative. The average input power is 13.833 watts, and the average output power is 3.277 watts. This gives us an efficiency of about 96%. Now let's find out where the power losses occur in our circuit. To speed things up, we can use a set of measurement statements to calculate the average power dissipation in each component, as well as the overall converter efficiency. Press Ctrl L to bring up the measurement log in LTspice. If we inspect the log, it turns out that the majority of the power losses are caused by the freewheeling diode. Let's understand why by plotting the diode current, voltage, and power. We'll also adjust the vertical scale of the diode power plot to ignore the short negative spikes and better visualize the average loss. The diode dissipates almost 0.5 watts, quite significant. The main contributor to the diode losses in a buck converter is the forward voltage drop when the diode is conducting. If we measure the forward voltage drop, we'll see it exceeds 800 millivolts, typical for a general-purpose diode. Let's replace it with a Schottky diode and rerun the simulation. We now see the forward voltage drop is down to around 350 millivolts. Bringing up the log, we can confirm that this has improved the converter efficiency to 97%. There are many more factors that influence converter efficiency, and we'll explore them in more detail in future videos. We'll also build more accurate models of the buck converter to analyze losses, conduction modes, and control schemes more deeply. That's a wrap on the buck converter. I hope you found this useful. Stick around for plenty more circuits to explore. This was All My Circuits.